Good morning. I'm Steve Wall, and this is Magellan at Venus. Magellan spacecraft playing a waiting game with the sun for the next few days. And meanwhile, scientists look at the relationship between two quite distinct processes that help to form the surface of our planet. We will talk more about those in a couple of minutes. First of all, let's let you know where the spacecraft is and how fast it's going. Currently, we're in our 654th orbit around the planet Venus at 44 minutes past apoapsis. So we're just completing the second half of a data playback. We would be completing if we were actually mapping right now, and we would be headed back for another mapping pass. As it is, of course, we're still waiting. We'll say more about that in a second. Distance to Earth is 159,313,000 miles. That's 256,389 and some change kilometers. Above the Venus surface, we are 6,354 kilometers. That's 3,948 miles. And we're traveling at 16,582 miles an hour. That's 22,953 kilometers an hour. Our transmissions take 14 minutes and 15 seconds to get from the planet back to Earth or the other way around, and that is the subject of our first story. We are still waiting to come out from the situation where the sun interrupts transmissions between the Earth and Venus, a situation called superior conjunction, where the sun is almost in a straight line, but not quite, with the Earth and Venus and in the middle. So what's happening is that the sun, as it gets into that line, stops transmissions, or we stop transmissions because the sun would interfere with them. Now that's a little bit hard to predict exactly how long that's going to happen. It sort of depends on what's happening on the outer limb of the sun, the place that the atmosphere would be on the Earth. And those flares that come up, sunspots, do interfere with radio transmissions. We have always had our slow but steady 40-bit per second engineering data, so we know that the spacecraft is still in good health. But the much higher 268,000 bits per second is not possible through these outer reaches of the sun, nor are dependable command transmissions. And so for that reason, we decided to take a break here. 16 days was the original estimate of how long that break would be. We actually stopped mapping on Friday, October 26th, but as I described last week, there were two reasons for stopping mapping. We also wanted to take a few days to look at a troublesome vibration of the solar panels. Well, we've taken this time to look at that problem and understand it now. We have diagnosed and have a solution ready, but we have to have a dependable command link before we can actually implement that fix. We tried yesterday some test commands to see if those commands would get into the spacecraft, but they didn't, or at least not all of them did. Mission Director Jim Scott decided that it was necessary to have a dependable command link, that is, all test commands into the spacecraft successfully before we actually went back to mapping. We'll try that again on Friday afternoon, and on Saturday morning, if everything works well, we'll be back into mapping. If there's still significant contribution from the sun to our telemetry errors, then we'll have to wait even longer. But we're coming out just about to the estimated 16 days of loss of data. And so we don't feel too badly about that. Things are actually going pretty well. In the meantime, the project has taken this time to catch up, to try to get some of the data products done. And the scientists have had a time where there are less meetings, less uplink responsibilities, if you will, and time to look at some data. Two processes that have been known to be important to the planet: the process of volcanism, of volcanoes that bring forth magma out of the surface, out of the interior of the planet, and the process of impact cratering, which is something that happens on all planets, have been found to have a strange suggestion of a relationship that we're going to talk about a little bit. So we've asked our project scientist, Steve Saunders, to come back and discuss that relationship with us. Steve, I see the first thing you want to talk about is not Venus at all, but something a little bit closer.
Well, this is just to remind everyone that the inner planets have something in common in their geologic history. They've all been bombarded over the last few billion years by bits of asteroidal debris, and craters have formed on their surfaces.
Okay.
A couple of interesting things about the craters on Venus are, one, we don't find any small ones. We think we understand that, and that's because objects that would form craters smaller than 2 or 3 miles in diameter don't make it through the dense atmosphere.
Okay, so the moon, which is what this is a picture of,
This is a picture
has no
of
atmosphere.
This is a picture of the far side of the moon with
Right.
its high density of impact craters.
And you see big ones,
Shoulder
you
to
see little
shoulder.
tiny ones, even as looks almost as small as you can see.
And they go all the way down to microns in diameter,
Okay.
dust spots.
Okay, but on Venus, all those little guys just get destroyed in the
they don't
atmosphere,
make it.
right? Okay.
And the other mystery about Venus is that we don't find very many large craters either, and the ones that we find are all relatively fresh, and that's one of the things I wanted to discuss a little bit today.
Okay.
I've got a picture of an area down in the southern hemisphere of Venus.
Okay. Okay, now this looks like one picture laid over another picture.
This is one of our what we call compressed mosaics. It's a pixel resolution of 225 meters. It covers an area of roughly 15 degrees on a side. That's about 1,500 kilometers.
Okay.
What we've done is we've laid in Earth-based Arecibo data here, which is 1 to 2 kilometer resolution, with many orbits of Magellan data here, which is our high-resolution mosaic, and we'll zoom in on some of those areas in a couple of minutes.
Okay, so what looks sort of fuzzy in our old knowledge of Venus is now really fine detail.
That's right.
Okay.
And what we're seeing here is a feature that we've talked about before called a corona. This one's about 400 miles in diameter. The best model so far for these is that they form over a hot spot in the interior, dome up, and over a very complicated history of volcanism and faulting at the surface, they evolve into this circular structure with very complex rim and complex inner volcanics.
Okay, so even though that
And,
looks sort of like an impact crater, it has nothing to do with impact. It's something inside.
It's as on Venus we have many kinds of circular features. Many of them are not impact craters, and we think we can tell the difference.
Okay.
Let's zoom in on a couple of areas here.
Okay.
Let's go up here in this region. We have, you recall we've talked about this feature before. We called it Gumby.
Okay.
And there turns out there's a chorus line of these features across here in more or less a line. And they're volcanotectonic features caused by probably the evacuation of magma from the subsurface and subsequent collapse.
Okay, this is the same thing that we talked about earlier, where the magma gets drained out from underneath and the top can't support itself.
That's
anymore,
right.
It just goes. Okay.
That's right. And notice over here, then, is a circular feature.
Okay.
This is most likely an impact crater. And we can say that because of the very rugged ejecta, which hasn't been completely destroyed by the volcanism here. And we'll
Okay.
get back to that in a few minutes. But
Okay.
this is the first good example that we've seen where we're finding a process that may destroy these craters. But we're going to move on down toward the south a little bit along these lines, which may or may not be associated with the corona. We're going to go down to the rim of the corona. And you can see these lines end up in fractures.
Yeah, okay, this is the edge of that corona we were looking at before.
That's right.
And here's the edge of the new data.
That's right. And we're heading into an area, a part of the rim in high resolution. This is apparently one of the earliest formed features here. We can work out a sequence of events that involves tectonism, that is faulting and mountain building, and volcanism, and then later fracturing. And then the latest thing that we see is this volcanism here, which is not cut by those fractures. And come in a little closer on that.
Okay, now this is just zooming in tighter, right?
On that.
That same thing.
Apparently
Here's
there's
this
a
new
moat around the outer rim of this corona
Okay.
that served as the site of the latest volcanism in the area. This is so fresh that it hasn't yet been cut by any of these fractures. And it's unlike a lot of the plains that we see elsewhere.
Wow. It's amazing. You can, just by seeing what intersects what, you can build a time history.
Then
here.
we can build up a sequence of events.
Because it wouldn't take long for this flow for these cracks to start showing through that flow?
Probably not,
Okay.
given that elsewhere on Venus we see that happening
Okay.
on most all the volcanic
I see.
flows that we see.
Okay.
Beginning to get a picture of a planet here that's in almost constant motion, and fractures are forming and reforming everywhere.
Okay, okay. So here's the newest flow now, and it's right on the rim of that corona.
Here you can even get up a little closer.
Okay.
See that in one place on that flow we do have a fracture, and this may be related somehow to the emplacement, but in general
Okay.
these fractures don't cross.
I see. Okay.
Now let's look toward the middle of the corona. In the center of it
Okay.
are a bunch of volcanic features here. And this is very interesting. This is a somewhat higher area. It's still a very complex region. You can see some of these collapsed depressions here.
Mm-hmm.
But what I wanted to point out here are these domes. And what this may be indicating is the evolution of the magma that's erupting onto the surface. In general, you don't get a steep-sided dome like these unless you have a fairly viscous, that is a thick magma. And geologically what that generally means is that it's more silicious and it's a more highly evolved, as we say, magma. And what it says is that the rock types are changing with time.
Okay.
And this is very important in understanding the evolution of these volcanics.
These domes came up through this new flow. I guess I'm still lost as where
The domes form by lava flows, basically, on top of this older surface. But it's a different
okay.
kind of lava that tends to form these steep-sided slopes.
Mm-hmm.
That is, it's much thicker, pastier lava.
Okay, and there's a basic difference between the silicious, the silicate formed
The
lava,
more silicious.
and the other kind. Are you saying that there's two distinct, different kinds of lava flow, or this is just a gradation term?
There may be many distinct types.
Okay.
What apparently happens in the magma chamber, either deep in the mantle of Venus or near the crust, is that with time these magmas evolve in composition. Maybe, for example, what happens is you get the latest magmas having more potassium in them, for example, which tends to produce a different set of minerals when they crystallize and make a steeper-sided volcano.
I get it. Okay.
I wanted to
big are
get
these
back.
guys? Just
These are on the order of 10, 15 kilometers across.
6 or 7
They're
miles.
not very large.
Okay.
Right.
Okay.
I'd like to get back to our crater story a little bit.
Okay.
Said earlier about how we don't get any of the very small craters. This one's about 12 kilometers in diameter.
Okay.
And just to remind everybody that what happens is that as the projectiles get smaller, they interact with the atmosphere. Perhaps they're crushed. Ultimately, they're vaporized in the atmosphere or pulverized in the atmosphere. And the smallest craters tend to have this very irregular shape.
Okay.
And as we get larger, they become more like the familiar craters on the moon.
Mm-hmm.
They all have a hummocky, rough ejecta, but they become more circular, and the floor becomes a little bit more regular.
Okay.
And then, as they get larger, way up to this size in the crater farm, the 60-kilometer diameter, this one's 40 miles across,
Okay.
they tend to develop central mountains and much more circular. But again, they all have this general fresh-looking morphology,
And some of them have black bottoms, which means they've had lava
probably
come
volcanic
into them, right?
material.
Huh.
So the real mystery here is what happened to all the other craters that we know surely formed on this Venusian surface at some time in the past, as they did on the moon, and why do all these look so fresh? Why don't we see a range of morphologies as we see on the moon and certainly on Earth?
And now we begin to find that maybe we have some sort of an answer to that.
Now we begin to
Some
see
sort of idea.
craters like this,
Yeah.
which are in the process or have been partly destroyed at some time in the past. We
Okay.
can't tell whether this is a continuing process here.
Okay, we're running out of time, so I guess we'll have to go on later on. But we'll talk more about the relationship between these processes next week. For now, I'm Steve Wall, and this is Magellan at Venus. We'll see you next week.